Good morning. Today we'll discuss continuation of last class. In last class we discussed relations. Okay? Relations. In that we discussed some all concepts of relations. Now I want to revise within 2 minutes all the concepts. What did we discuss? Ordered pair, Cartesian product. Ordered pair, Cartesian product, relation, inverse relation, identity relation, empty relation, universal relation, reflexive relation, symmetric, transitive, equivalence. Okay. We discussed these concepts. Once I want to revise within 2 minutes. Ordered pair. What is ordered pair? A comma B. This is called ordered pair. Here, first element belongs to first set, second element belongs to second set. Cartesian product. What is Cartesian product? Set of all ordered pairs from first set to second set. In generally, it is denoted by A cross B. What is its value? A comma B such that A belongs to A, B belongs to B. Okay. This is Cartesian product definition. Next, relation. Any subset of a Cartesian product A cross B is a relation from A to B. Okay. Any subset of a Cartesian product is called a relation from A to B. That is, R is a relation, that is a subset of A cross B. Clear? Next, inverse relation. So R is a relation, its inverse is denoted by R inverse. What is its value? B comma A such that A comma B belongs to R. This is the definition of inverse relation. Here, the element of A R inverse is in the form of B comma A, where A comma B belongs to R. Next, identity relation. So a relation is of the form A comma A such that A belongs to A is called an identity relation on A. Here capital A is the set. The relation is of the form A comma A such that A belongs to A. So this relation is called identity relation. Already we discussed it in last class. No problem. Empty relation. So what is actually relation? It is a subset of Cartesian product. Now I am taking Cartesian product A cross A. In that, null set is a subset. Correct? Null set is subset of Cartesian product. So null set is a relation. Especially this relation is called empty relation. Okay. Next, universal relation. So A cross A is subset of A cross A. Can we agree? Every set A cross A is a set. Cartesian product, whatever it may be, it is also one of the set. Thus, that set is subset to itself. So A cross A is subset of A cross A. So a subset of A cross A is a relation. So A cross A is a relation. Especially this relation is called universal. Universal relation on A. So A cross A is universal relation on A. Next, reflexive relation. What is reflexive relation? A comma A belongs to R for all A belongs to A. Okay. If any relation R satisfies this condition, that is A comma A belongs to R for all A belongs to A, then R is said to be reflexive relation. Next, symmetric relation. If A comma B belongs to R implies B comma A belongs to R. If AB belongs to R, then we have to prove BA also belongs to R. That is, if AB belongs to R implies BA belongs to R, then we can say R is symmetric. Okay. Next, transitive. If A comma B belongs to R, B comma C belongs to R, implies A comma C belongs to R. Any relation satisfies this condition. If AB belongs to R, comma BC belongs to R, implies AC belongs to R. If these two belongs to R, then AC also belongs to R. Any relation satisfies this condition, that relation is called transitive relation. Next, equivalence relation. What is equivalence relation? A relation which is reflexive, symmetric, and transitive. So any relation satisfies these three relations, that relation is called equivalence relation. So we have given some formulas also. Number of relations formula. Number of relations formula 2 power pq. Here p is number of elements in A, q is number of elements in B. So number of relations formula 2 power pq. So number of relations from set A to set B, that is formula. Next, number of relations on A means set A to A, that is 2 power m into m, that is 2 power m square. Here first set elements are p, m, second set elements also m. So m into m, 2 power m into m, that is 2 power m square. Number of reflexive relations on A, m into m minus 1, 2 power m into m minus 1. This is formula for number of reflexive relations on set A, where A has m elements. So number of elements in A is m elements. Next, 2 power m into m plus 1 by 2. This is formula for number of symmetric relations on set A, where A is a set which contains m elements. Okay. Next, one more important formula we discuss. If A intersection B is equal to m, means number of common elements in A and B is m, then number of common elements in A cross B and B cross A is m square. Okay. In last class we discussed all these concepts. Now we will do problems on these concepts. So in last class we did one problem also. Now continuation. Determine. First question already completed. In first bit, have bits you can verify. In first bit, first question completed. Now second question. Check it. R is a relation on set natural numbers. Set of natural numbers. So what is the given set? Natural number set. And defined as R is equal to, the relation is given like this one, x comma y such that y is equal to x plus 5, where x is less than 5. So a relation is given on set n. So it is defined like this one. R is equal to x comma y such that y is equal to x plus 5, where x is less than 4. So we have to check this relation is reflexive, symmetric, and transitive. We have to check the three relations. Now, first of all, have to write this is finite set now, because x value is less than 4. X value less than 4 means x should be 1, 2, 3 only. So x belongs to x values are 1, 2, 3, because x is a natural number. Natural number that is less than 4. So x values are 1, 2, 3. So first put x equal to 1. What will happen? What is y condition actually? X plus 5 only. Put x equal to 1. What is y value? 1 plus 5. That is 6. X value 1, y value 6. So first element is 1 comma 6. Put x equal to 2. What is y value? 2 plus 5. That is 7. X value 2, y value 7. So 2 comma 7. Next, third, put x equal to 3, y equal to 3 plus 5. That is 8. So third element is 3 comma 8. So this is given relation in roster form. Okay. This is the given relation in roster form. Now we have to check it satisfies relation reflexive, symmetric or not. We have to check now. So it satisfies reflexive, symmetric and transitive. We will go for one by one. First, reflexive. Is it reflexive or not? No, it is not reflexive. Why? Because what is the condition of reflexive one? A comma A belongs to R for all A belongs to A. So A belongs to given set, then A comma A belongs to R. What are the elements in A? What is the given set? 1, 2, 3 only. So the elements in A given set is 1, 2, 3. So there should be 1, 1, 2, 2, 3, 3. So there is no 1, 1, there is no 2, 2, there is no 3, 3. So it is not reflexive. Correct? Yeah. Actually, reflexive means there should be 1, 1, 2, 2, 3, 3. Because reflexive definition, A comma A belongs to R. Here, it is not possible. No? So if it is not reflexive, we have to give one example. So for 1 belongs to capital N. So given set is N, but 1 comma 1 does not belongs to R. Therefore, R is not reflexive. R is not reflexive. First one clear now. Next, go for symmetric. Is it symmetric or not? What is the definition of symmetric? If AB belongs to R, implies BA also belongs to R. See here, what are the elements in R? 1, 6. If AB is there, there should be BA also. 1, 6 is there, 6, 1 is not there. So, no need to check other elements. Simply, we can write 1 comma 6 belongs to R, but 6 comma 1 does not belongs to R. Clearly, 1 comma 6 belongs to R, but 6 comma 1 does not belongs to R. Therefore, R is not symmetric. Because what is the definition of symmetric? If AB belongs to R, compulsory BA also belongs to R. But here 1, 6 belongs to R, but 6, 1 does not belongs to R. So condition is not satisfied. That's why R is not symmetric. Next, go for transitive. What is definition of transitive? If AB BC belongs to R, then AC belongs to R. If AB comma AB belongs to R, BC belongs to R, then AC belongs to R. Check it now. AB 1, 6. Next to BC. Is it possible any other BC? No, it is not possible. So actually, if it is not transitive, means we have to give an example. So it is not possible to give an example. That's why I will write a general definition. If A comma B belongs to R, comma B comma C belongs to R, implies A comma C belongs to R. Therefore, R is transitive. So don't get confused, because this is some, you will get some contradiction. Actually, what is the definition of transitive? If AB BC is there, then we have to prove AC also there. See, if just take any elements AB and BC, then I will prove AC also there. So here it is not possible to get AB and BC. That's why no need to prove AC. That's why directly I have written A. If AB BC is there, compulsory we can prove AC also there. That's why it is clearly it is transitive. Clear? Second question. Go for third question. R is the relation on set A. 1, 2, 3, 4, 5, 6. So relation is defined like this now. R is equal to x comma y such that y is divisible by x. So this is the given relation. Now we have to check it is reflexive, symmetric, and transitive. Okay, we'll check one by one. First of all, it is a finite set. If it is finite set, we have to write all the elements which satisfies this condition. Okay, R is a relation on A. On A is nothing but R is relation from A to A. So that is 1, 2, 3, 4, 5, 6 to 1, 2, 3, 4, 5, 6. Okay. Now check one by one. First element I am taking 1, comma 1. 1, comma 1. So first element belongs to first set. Second element belongs to second set. First I will take 1, comma 1. Is it satisfies or not? Just check it. Y is divisible by x. Here what is y? 1. What is x? 1. So 1 is divisible by 1. Yes, it is true. One is divisible by 1. Yes, 1, comma 1 is satisfies. Next, go for 1, comma 2. 1, comma 2. Is it correct or not? Here x, this is y. Check now. Y is divisible by x. That is 2 is divisible by 1. Correct. It is also possible. Next, go for 1, 3. 1, 3. 3 is divisible by 1. Correct. 3 is divisible by 1. It is possible. Next, 1, 4. 4 is divisible by 1. Correct. 1, 5. 5 is divisible by 1. Correct. Next, 1, 6. 6 is divisible by 1. It is also correct. Next, one combination. What? Next, go for two combination. 2, 1. Take 2, comma 1. 1 is divisible by 2. Is it right now? No, it is not possible. 1 is divisible by 2 is not possible. Only 2 is divisible by 1. It is possible, but 1 is not. This is x, this is y. Nah? So what is the condition? Y is divisible by x. Here this is y, this is x. Check the condition. 1 is divisible by 2. No, it is not possible. So 2, comma 1 is not there in the relation. Next, go for 2, comma 2. Yes, check it now. Here x, y. Y is divisible by x. 2 is divisible by 2. Right, it is possible. Next, go for 2, 3. 3 is divisible by 2. Wrong. 3 is divisible by 2 is wrong. So 3, 2 is not possible. Next, go for 3, 4. 2, 4. 4 is divisible by 2. Yes, it is possible. Similarly, 2, 5 is not possible. 2, 6 is possible. 6 is divisible by 2. So 2 combination. Next, go for 3 combination. 3, comma 1. 1 divisible by 3. Wrong. So 3, 1 is not possible. Go for 3, 2. 2 is divisible by 3. Wrong. So 3, 3. 3 is divisible by 3. Yes, it is possible. Next, go for 3, 4. 4 is divisible by 3. Not possible. 3, 5. 5 is divisible by 3. It is not possible. 3, 6 is possible because 6 is divisible by 3. Next, go for 4 combination. 4, 1. 1 is divisible by 4. Wrong. 4, 2. 2 is divisible by 4. Wrong. 4 is divisible by 2, but 2 is not divisible by 4. So 4, 2 also not possible. 4, 3 also not possible. 4, 4 possible. Next, 4, 6. Right? 4, 6. 6 is divisible by 4. It is not possible now. 6 cannot be written as 4 into something. Yes, it is not possible. So 6 is divisible by 4 is wrong. So 4 combination over. Next, similarly, 5, 1, 5, 2, 5, 3, 5, 4 not possible. Only 5, 5 is possible because 5 is divisible by 5. It is possible. Okay. Next, go for 5, 6. 6 is divisible by 5. It is not possible. Next, 6 combination. 6, 1. 1 is divisible by 6. Wrong. 6, 2. 2 is divisible by 1. Wrong. 6, 3. 3 is divisible by 6. Wrong. 3, 6, 4, 6, 5 also not possible. Only there is a possibility 6, 6. So these are the elements in the relation. Okay, these are the elements in the relation. Now go for reflexive, symmetric, and transitive. First of all, is it reflexive or not? Reflexive means A comma A belongs to R. What are the A values? 1, 2, 3, 4, 5, 6. So A values are 1, 2, 3, 4, 5, 6. So A comma A means 1, 1. Yes, it is there. Next, 2, 2. It is there. 3, 3, 4, 4, 5, 5, 6, 6. All the elements are there now. So no need to write all the elements. No? We can write general definition. So clearly, A comma A belongs to or for all A belongs to capital A. You can take any A belongs to A, means 1, 2, 3, 4, 5, 6, we'll get A comma A belongs to R. If you take 1 is there. If you take 2 is there. 3 is there. 4 is there. 5 is there. 6 is there. So all the elements are there. So clearly A comma A belongs to R, for all A belongs to A. Therefore, R is reflexive. Next, go for symmetric. Is it symmetric or not? Symmetric means, what is symmetric? If AB belongs to R, implies BA also belongs to R. So if AB is there, BA should be here. 1 AB, BA also 1. So it is possible. Next, go for another element. 1 2 is there. Is there 2 1? No. So AB is there, BA is not there. So if you get one element also, it is not symmetric. So here clearly 1 comma 2 belongs to R, but 2 comma 1 does not belongs to R. Therefore, R is not symmetric. R is not symmetric. Go for transitive. What is transitive definition? If AB belongs to R, BC belongs to R, implies AC belongs to R. So take AB, any AB, 1 1, AB. Next one combination 1 3. So 1 1 1 2, AB BC. AC means 1 2. Yes, it is there. AB. Next BC. Now AB BC. AC means 1 3. Yes, it is there. 1 1 1 4. 1 4 is there. 1 1 1 5. 1 5 is there. 1 1 1 6 means 1 6 also there. Next, go for another element, just for our observation. Just we can check. AB value 1 2. I'm taking 2 combination. Next to 2 combination 2 2. 1 2 2 2 means 1 2. Yes, it is there. 1 2 2 4. AB BC AC. That is 1 4. It is there. 1 2 2 6. 1 2 2 6. AB BC AC 1 6. Yes, it is there. Next. Okay, 2 combination 1 3. Next 3 combination 3 3. 1 3 3 3. AB BC AC, that is 1 3. This is next 1 3 3 6. AB BC AC 1 6. Yes, it is there. So check all the elements satisfies the condition. So verify this clearly. A comma B belongs to R, comma B comma C belongs to R, implies A comma C belongs to R. Therefore, R is transitive. R is transitive. Is it equivalence relation? No. Because when we say equivalence relation, if it is reflexive, symmetric as well as transitive. But it is reflexive and transitive, but not symmetric. So it is not equivalence relation. Next, go for fourth question. This is important. R is a relation on set Z. Integers. Z means integers. So the relation is defined like this. R is equal to x comma y such that x minus y is an integer. X minus y is an integer. So in this case, we cannot write all the elements now because it is a infinite set. Z is infinite set. If it is infinite set, we can't write all the elements. In this case, we have to follow the general method. So go for reflexive. Reflexive. What is reflexive one? Okay, here xy is there, so we have to prove x comma x belongs to R. Correct na? What we have to prove? X comma x belongs to R. Substitute in that. In place of y, put x. What will happen? Put y equal to x1. What is the condition? X minus x is an integer. Is it right or wrong? Yes, it is possible. Just try to understand. What we have to prove? X comma x belongs to R. Is it possible or not? When we take x comma x belongs to R, if x comma x satisfies this condition, put y equal to x. What will happen? X minus x is an integer. Yes, correct. For x belongs to z, means for any integer z, x minus x. What is x minus x from? 0 is an integer. Correct now? Is an integer. So x minus x is an integer, means x comma x belongs to element condition. So x comma x satisfies the condition. X comma x is element of R. So x comma x belongs to R. Therefore, R is reflexive. Next, go for symmetric. Is it symmetric or not? We have to check. No? Okay. Symmetric. So, what is symmetric? No? If x comma y belongs to R, we have to prove y comma x belongs to R. So if you take AB, then we have to prove BA. If you take xy, then we have to prove yx belongs to R. Check it now. First of all, x comma y belongs to R means what? X minus y is an integer. So if element is there in the relation, that element satisfies the condition. So that's why I am writing x minus y is an integer. Can we agree, man? If 3 is integer, then minus 3 is also integer. Can we agree? If any integer is there, by multiplying with negative sign, then also it is integer. See here, x minus y integer, that's why minus of x minus y is an integer. Correct now? X minus y integer means minus of x minus y also integer, because 3 is integer, minus 3 is also integer, means by multiplying with negative sign, then also it is integer. Next, minus of x minus y is nothing but minus x plus y, or we can write y minus x is an integer. Correct or x minus y integer means x comma y belongs to R. Y minus x is an integer means y minus x belongs to. Correct? First we have taken x comma y belongs to R. Now we proved y comma x belongs to R. That's why R is symmetric. Next, go for transitive. What is transitive? If x comma y belongs to R, y comma z belongs to R, then we have to prove x comma z belongs to R. So what we have to prove? X comma z belongs to R. Okay. How can we prove x comma z belongs to R? First of all, x comma y belongs to R means what? X minus y is an integer. From definition. Here, x comma y belongs to R means x minus y is an integer. Next, y comma z belongs to R means x comma y belongs to R means x minus y integer. Y comma z belongs to R means y minus z is an integer. So we can take y minus z is an integer. Correct now? So just check it now. 4 is integer, 6 is integer. Then sum of these two also integer. Can we agree? If 4 is integer, 6 is integer, 4 plus 6 is also integer. Can we agree? Yes. In the same way, x minus y integer, y minus z integer. Sum of these two integers is again integer. That's why I am taking like this. X minus y plus y minus z is an integer. Can we agree? Yes, it is possible. So minus y plus y cancel. What can we conclude now? X minus z is an integer. Correct? X minus z is an integer. So if x minus y integer, then we can say x comma z belongs to x comma y belongs to R. Here in place of y, what is there? Z. So x minus z is an integer. So directly we can write x comma z belongs to R. First we have taken x minus y, x comma y belongs to R, y minus y comma z belongs to R. Now we prove x comma z belongs to R. Therefore, R is transitive. Observe now. R is reflexive, R is symmetric, R is transitive. So any relation satisfies these three relations, then we can say R is an equivalence relation. So directly we can say R is an equivalence relation. R is an equivalence relation. So, similar question is there in example. So we'll discuss that same question. That is also very, very important question. See, example 5. If you have books, you can verify. Page number 3. Example 5. See, show that. I will write question also. Show that the relation capital R in the set capital Z of integers given by R is equal to A comma B such that 2 divides A minus B. 2 divides A minus B is an equivalence relation. This is the question. Now we have to prove this relation is an equivalence relation. Okay, we will check now. First, given information I will write now. Set. What is set now? Z integers. Given set is set of integers. Next, relation. How they define relation? R is equal to A comma B such that 2 divides A minus B. So here what is the element now? A comma B is the element. What is the condition? 2 divides A minus B is the condition. So already we discussed the meaning of this one. If A comma B belongs to R, then we can use 2 divides A minus B. In other words, if 2 divides A minus B, then we can use A comma B belongs to R. Correct now? Element is there in the relation. That element satisfies the condition. If element satisfies the condition, then that element belongs to R. Okay. Now we will check one by one. Reflexive. Is it reflexive or not? Just what we have to prove. A comma A belongs to R. So when it is possible, A comma A belongs to R. A comma A belongs to R means put A equal to B. So B equal to A. What will happen? 2 divides A minus A. Is it possible? Yes, it is possible. So I will write one clearly. For every A belongs to Z, 2 divides A minus A. That is 0. 2 divides 0. 0 is divisible by 2. Yes, it is possible. 2 divides A minus A. That is 0. 2 divides 0. It is possible because 0 can every element 0 is divisible by every element. So 2 is also 2 divides 0. Try to understand. No? 2 divides A minus B, then we can say A comma B belongs to R. Now 2 divides A minus A means A comma A belongs to R. So directly we can write A comma A belongs to R. Therefore R is reflexive. Why it is reflexive? Because A comma A satisfies the condition. What is the condition? 2 divides A minus A. That's why A comma A belongs to R. If 2 divides A minus B, then we can write A comma B belongs to R. But 2 divides A minus A means A comma A belongs to R. That I have written. Next, go for symmetry. If A comma B belongs to R. From definition, if A comma B belongs to R, then we can use 2 divides A minus B. So we can use 2 divides A minus B. Just check it one. See here, 10 divides 2. Correct? 10 is divisible by 2. So 10 is also divisible, minus 10 is also divisible by 2 because 2 into minus 5 is equal to minus 10. Is it? Means if a minus b, 2 divides a minus b, then we can say 2 divides minus of a minus b also. That implies we can write it. 2 divides minus of a minus b also. Check it one, just for example. 2 divides 10. 2 divides minus 10 also. Because remainder is 0. Na? In the same way, 2 divides a minus b, then 2 divides minus of a minus b also. That means 2 divides minus of a minus b. Minus of a minus b means minus a plus b, or we can write b minus e. If 2 divides a minus b, then we can say a comma b belongs to R. 2 divides b minus a means b comma a belongs to B comma A satisfies the condition. B comma A belongs to R. Therefore, R is symmetric. R is symmetric. Next, go for transitive. Transitive. Try to understand. No? Transitive. What is transitive? If A comma B belongs to R, comma B comma C belongs to R, then we have to prove A comma C belongs to. We have to take these two and we have to prove this one. Correct? Check it. First, A comma B belongs to R means we can use 2 divides A minus B, comma B comma C belongs to R means 2 divides B minus C. Just try to understand. 2 is divides 4, 2 divides 6. Correct? 2 divides 4, 2 divides 6. Then 2 divides 4 plus 6. That is 10. Correct now? If 2 divides 4, 2 divides 6, then 2 divides 4 plus 6 also. In the same way, 2 divides A minus B, 2 divides B minus C, then 2 divides A minus B plus B minus C also. Means sum of two integers is also divisible by 2. If two integers are divisible by 2, then the sum of those two numbers integers divisible by 2 also. So minus B plus B cancel. What can you conclude now? 2 divides A minus C. So 2 divides A minus B means we can say A comma B belongs to R. 2 divides A minus C means A comma C belongs to R. So first we have taken A comma B belongs to R, B comma C belongs to R. Now we prove A comma C belongs to R. Therefore, R is transitive. R is transitive. Observe, huh? R is reflexive. R is symmetric. R is transitive. Therefore, R is an equivalence relation. Equivalence relation. Okay. See, example 2. Let capital T be the set of all triangles. Set of all triangles in a plane. With R is a relation. With R a relation. With R a relation in T given by R is equal to T1 comma T1 such that T1 is congruent to T2. Show that R is an equivalence relation. Show that R is an equivalence relation. Okay. Try to understand. First of all, what is given set? Set T is equal to, okay, set, what is T1? T is set of all triangles in a plane. T is equal to set of all triangles, set of all triangles in a plane. This is given. Relation, how they define? T1 comma T2 such that T1 is congruent to T2. Okay. This is a given relation. This is given set. Using these two informations, now we have to prove the relation is an equivalence relation. Now try to understand it. First of all, see here. What is the element here? T1 comma T2 belongs to R. This is the element. What is the condition? T1 is congruent to T2. Actually, what are the congruent angles? The corresponding sides and corresponding angles are equal. Okay, na? Corresponding angles are equal. Corresponding sides also equal. Then the two triangles are said to be congruent triangle. That relation is, we have to prove that relation is an equivalence relation. Now, we will check one by one. First, reflexive. Is it reflexive or not? For any triangle T1, T1 belongs to capital T, means for any triangle T. T, what is T1? Set of all triangles. Huh? In that all triangles, for any triangle T1, T1 is congruent to T1. Correct? No? Is it possible? A triangle is congruent to itself. We can take any triangle, that triangle is congruent to itself. T1 is congruent to T2, then we can say T1 comma T2 belongs to R. T1 is congruent to T1. That implies T1 comma T1 belongs to R. For all T belongs to T. For any triangle T1, T1 is congruent to T1. Yes, it is possible. A triangle is congruent to itself. Yes, it is possible. So T1 comma T1 satisfies the condition. T1 comma T1 belongs to R. Yes. Therefore, R is reflexive. Actually, reflexive means A comma A belongs to R. Na? So the elements in the form of T1 comma T2. Na? That's why I am taking T1 comma T2. If X comma Y, X comma X. If P comma Q, then we can say P comma P like that. Here T1 comma T2 form. That's why I have taken T1 comma T1. If it is in the form of A comma B, then we have to prove A comma A belongs to R, like that. Okay, just symbols. The concept is same. Symbols may be changes. Next, go for symmetry. What is definition of symmetry? If AB belongs to R, then BA also belongs to R. Now, if first take this one, T1 comma T2 belongs to R. What is the meaning of T1 comma T1? T1 comma T2 belongs to R means T1 is congruent to T2. So we can say T1 is congruent to T2. If first triangle is congruent to second triangle, then we can say second triangle is also congruent to first triangle. That's why we can take T2 is congruent to T1. So we can take T2 comma T1 belongs to R. Therefore, R is symmetric. Just don't get confused. Very simple. First, if T1 comma T2 belongs to R, element is there in the relation. What is the meaning? T1 is congruent to T2. Okay, just check it now. This is first triangle. This is second triangle. This is T1. This is T2. These two are congruent. Means first one, second one are congruent. Then second one, first one also congruent. Nah, there is no change. Okay, corresponding sides are equal, compulsory equal. Corresponding angles also equal. So, for example, this is 3 units, 4 units. Here also 2 units, 3 units, 4 units. 2 by 3 equal to 3 by 3 equal to 4 by 4. Then 2 by 2 equal to 3 by 3 equal to 4 by 4. It is also possible now. So T1 congruent to T2 means compulsory T2 is also congruent to T1. No need to check now. Directly we can say. Okay. Next, go for transitive. What is transitive? If T1 comma T2 belongs to R, comma T2 comma T3 belongs to R. Now we have to prove T1 comma T3 belongs to R. First, T1 comma T2 belongs to R means T1 is congruent to T2. T2 comma T3 belongs to R means T2 is congruent to T2. Just try to understand. This is first triangle, second triangle, third triangle. T1, T2, T3. These two are congruent. These two are congruent. Means compulsory. These two also congruent. Okay. So we can say T1 is congruent to T3. T1 comma T3 satisfies the condition. T1 comma T3 belongs to R. Therefore, R is transitive. R is transitive. Let's try to understand. R is reflexive. R is symmetric. R is transitive. Therefore, R is an equivalence relation. R is an equivalence relation. Hence, correct? Next, go for example 3. This is also important one. Let capital L be the set of all lines in a plane. Set of all lines in a plane or with the relation in L defined by R is equal to L1 comma L2 such that L1 is perpendicular to L2. Show that R is symmetric. Show that R is symmetric, but neither reflexive nor transitive. This is a question. Try to understand. It is a very simple question. Here, first of all, what is given set one? L. L with the given set. What is L1? Set of all lines in a plane. So L is set of all lines in plane. Okay. So in L, all lines are there. Okay. Now relation, how they define R is equal to L1 comma L2 such that L1 is perpendicular to L2. They define like this. First, try to understand the relation. Here, what is the element? L1 comma L2 is the element. What is the condition? L1 perpendicular to L2. This is condition. This is element. Correct? Now, first try to understand. What is the meaning? L1 comma L2 belongs to R. Means element is there in the relation. Then it satisfies the condition. That is, L1 is perpendicular to L2. In other words, reverse case. If L1 is perpendicular to L2, then we can say L1 comma L2 belongs to R. Okay? Now, go for reflexive. What we have to prove? It is not reflexive, not transitive, but it is symmetric. So check it. Simply we can follow. We'll get it. First of all, reflexive means what? L1 belongs to R. Just to substitute in place of L2, substitute L1. What will happen? L1 is perpendicular to L1. A line is perpendicular to the same line. Is it possible? No, it is not possible. Check it, ma. This is first line, ma. This line is perpendicular to this line. Wrong. It is not possible. A line cannot be perpendicular to itself. Correct? I am taking one line. Any one line. L1 in L. L1 is perpendicular to L1. It is not possible. Correct? So that's why I am writing this one. For L1 belongs to L. In L, what are there? Lines. All lines are there. In that, I am taking one line. L1 is any line. So we can say L1 is not perpendicular L1. Correct? A line cannot be perpendicular to itself. So L1 is not perpendicular to L1. Correct? So L1 is perpendicular to L1, then we can say L1 comma L1 belongs to R. L1 is not perpendicular to L1 means L1 comma L1 does not belong to R. So L1 comma L1 does not belong to R. A comma A does not belong to R. Then R is not reflexive. Therefore, R is not reflexive. Here, next, go for symmetry. What is symmetry? If L1 comma L2 belongs to R. What is the meaning of L1 comma L2 belongs to R? L1 is perpendicular to L2. Just observe. This is first line. This is second line. L1, L2. L1 is perpendicular to L2. Then we can say L2 is also perpendicular to L1. Correct? Na? If L1 perpendicular to L2, we can say L2 is also perpendicular to L1. So directly we can write L2 is perpendicular to L1. So L2 comma L1 satisfies the condition. So L2 comma L1 belongs to R. First we have taken L1 comma L2 belongs to R. Now we proved L2 comma L1 belongs to R. Therefore R is symmetric. Next, go for transitive. Transitive. Okay. Transitive. What is transitive? If L1 comma L2 belongs to R, L2 comma L3 belongs to R. Okay. Now we have to prove L1 comma L3 belongs to R. If it is belongs to R, then we can say it is transitive. If it is not belongs to, then it is not transitive. Just first book one. L1 comma L2 belongs to R means what? L1 is perpendicular to L2. L2 comma L3 belongs to R. Element. What is the condition? L2 is perpendicular to L3. Observe, this is first line, second line, third line. L1, L2, L3. What can we say? L1 perpendicular to L3. These two lines are perpendicular. L2 perpendicular to L3. These two lines are perpendicular. What about L1 and L3? These are parallel. Parallel means not perpendicular. Correct? Na? L1 perpendicular to L2. L2 perpendicular to L3. But L1, L3 are parallel, not perpendicular. So we can say L1 perpendicular to L2, L2 perpendicular to L3. Then L1 is not perpendicular to L3. So if it is perpendicular, we can say belongs to. If it is not perpendicular, means not belongs to. L1 comma L3 does not belongs to R. Therefore, R is not transitive. So what is the conclusion? The relation is symmetric, but neither reflexive nor transitive. Next, example 4. Show that the relation. Show that the relation R in the set. The set 1, 2, 3 given by I is equal to 1 by 1, 2, 1, 2, 3, 3, 1, 2, 2, 3 is reflexive but neither symmetric nor transitive. Just try to understand. A relation is given. First, R is a relation. A is the set. What is the set now? 1, 2, 3. I'm taking A equal to 1, 2, 3. This is the given set. Next, relation. How they define? R is equal to 1, 1 is there, 2, 2 is there, 3, 3, 1, 2, 2, 3. Now we have to prove this relation is reflexive but neither symmetric nor transitive. We go over one by one. Reflexive. Is it reflexive, ma? Yes, it is reflective clearly. Why, ma? 1, 2, 3 there in the set, ma. So R should be contains 1, 1, 2, 2, 3, 3. Yes, 1, 1 is there, 2, 2 is there, 3, 3 is there. What is the definition of reflexive, ma? A comma A belongs to R. For all A belongs to A. So what are the elements in A, ma? 1, 2, 3. So R must contains 1, 1, 2, 2, 3, 3. All the elements are there, ma? Clearly it is reflexive. Clearly. A comma A belongs to R. A comma A belongs to R. For all A belongs to A. Means A belongs to A means what are the elements in A? 1, 2, 3. A comma A means 1, 1, 2, 2, 3, 3. It is there now. So only 3 elements are there. We can write all the elements also. No? In general, we can write like this. Therefore, R is reflexive. Next, go for symmetric. Is that symmetric or not? We have to prove it is not symmetric. Not symmetric means we have to give one example. Okay, check it out. Here 1, 2 is there, but 2, 1 is not there. What is symmetric definition? Ma? AB belongs to R implies BA belongs to R. But here 1, 2 is there, 2, 1 is not there. Therefore, it is not symmetric. Just we will give one example which does not satisfy the condition. So, clearly, if 1, 2 belongs to R, but 2, 1 does not belongs to R. So AB is there, BA is not there. Therefore, R is not symmetric. It is not symmetric. Go for transitive. Transitive relation. What is transitive relation? If AB belongs to R, comma BC belongs to R, then implies AC belongs to R. So, but we have to prove it is not transitive. Not transitive means we have to give one example. So, see that one. 1, 2 is there, 2, 3 is there. AB, BC. What is AC, ma? 1, 3. AB, BC, AC. 1, 3. 1, 3 is not there, na? So, it is not transitive. So, I will give one example. Clearly. If 1, 2 belongs to R, 2, 3 belongs to R, but 1, 3 does not belong to R. Therefore, R is not transitive. Clear now? AB, BC, AC. AB is there, BC is there, but AC is not there. Therefore, it is not transitive. Okay, just go through it, ma, all the problems and the concepts also. Tomorrow is exam is there on these concepts only on relations concept. Ma. Some synopsis are given in last class, so go through it all the synopsis also. Ma. We have CET also on those concepts. Okay, I will give information and material also. Ma. So just go through it once. Okay, we'll discuss in the next class. Thank you.